Hi. In this video, we're going to go through a few worked problems solving linear systems using the tool of Gaussian elimination. For each problem we present, I strongly recommend that you pause the video when we present the problem, work through it on your own, then restart to follow along the solution and compare to your own work. The first problem we're going to look at, trying to find the solution or to demonstrate there is no solution to the system of equations given here. We're going to address this problem using standard Gaussian elimination following the strict order of operations for this method. We always start in Gaussian elimination with the top row and the right or the leftmost variable to consider as a pivot. This position here, negative 2x, we wish to use as a pivot to eliminate entries below. We have a coefficient of 1 in the second row, so in order to eliminate using the first, we need to add 1/2 of the first row to that second row. We have a coefficient of 3 in the third row and a coefficient of negative 2 in the first. So to eliminate this 3x using the first row, we need to multiply the first row by 3/2 and then add it to the third row. Executing on that, we see we have x. Remember, for this second row, we're multiplying by 1/2, the first row by 1/2 and adding. So x minus x is 0. Y plus y is 2y. Negative z minus 1/2 z is negative 3/2 z. 2 plus 1/2 is 5/2 for the right-hand side. For the third row, we're multiplying the first row by 3/2 and adding. 3x minus 3x is 0. 2y plus 3y is 5y. And 2z minus 3/2 z is 1/2 z. For the right-hand side, 3 plus 3/2 is 9/2. We have now successfully pivoted away the whole entire first column with the exception of this first variable. There is nothing below this first pivot. We now move down to the next row, over to the next column, and put our attention at the next possible pivot. We want to use this entry of 2y to eliminate the entry below. We have a coefficient 5 on the third row, a coefficient 2 on the first. In order to eliminate using this second row, we need to divide the second row by 2 and then multiply by 5. That is, multiply by 5/2. And then we can subtract the result from the third row. Subtract 5/2 of the second equation from the third. 5 minus 5y minus 5y gives 0. 1/2 minus negative 3/2 times 5/2 is 1/2 plus 15/4 times z. We'll simplify this on the next slide. On the right-hand side, 9/2 minus 5/2 times 5/2. 9/2 minus 25/4, which we will also simplify on the next slide. Moving forward with the simplifications in place, we now recognize that we're in an upper triangular form. We have a pivot in the first position, the x position for the first row, a pivot in the y position for the second, a pivot in the third position of the third row. Every variable is a pivot. This means that this system has a unique solution. This system has a single unique solution. We can find it following through the rules for back substitution. Back substitution, we start at the bottom with our attention towards the right of the system, the pivot and that variable of the bottommost row. And we want to solve for this pivot of z. If 19/4 times z is equal to -7/4, then z must be equal to -7/19. After solving for z, we can substitute that value back into the two positions where there is a z in equations above that. Negative z becomes +7/19. -3/2 z becomes -3/2 multiplied by -7/19, which we'll simplify again on the next slide. After solving and substituting z, we shift our attention up a row to the left of the system to the next pivot, y, in the second row. Y is isolated now in this second equation. We can solve for it. 5/2 minus 21/38, so we move that over, then divide through by the remaining 2. 1/2 times 5/2 minus 21/38 gives us, with a tiny bit of arithmetic, 37/38. We then substitute that value again back into the places above it where there is the y. 2y becomes 2 times 37/38, or 37/19. Moving forward, we now move up to one equation, over to the left to our next and final pivot. X has now been isolated as the only variable on this row, and we solve for it. 1 minus 37/19, moving that piece over, minus 7/19, moving the other piece over, and then dividing through by -1/2. -1/2, 1 minus 37/19 minus 7/19 gives 29/38 for our value for x. Because this is our last variable, there's no substitution to do with this piece. We actually now have our final answer, x, y, z, and our set of answers. Thus, our final answer for the system, we can either write it as a set of individual values for the variable, or in vector form as x, y, z equals 29/38, 37/38, and -7/19. Or if you prefer, we can factor out a 1/38 and have whole numbers in the vector. A unique solution for this system. One thing that you might note is the system when we started off looked pretty straightforward. It didn't look like it was particularly complicated. The numbers that we had, the coefficients, were all small integers. It is very easy, even in seemingly straightforward problems, for the arithmetic to lead to relatively large denominators and a little bit of a mess in terms of working through the arithmetic. This is one of the reasons why for real-world problems in linear algebra, we almost always solve them using the aid of computers rather than by hand. It still is helpful, both in terms of developing intuition and understanding how these computer solutions work, to get the practice to learn how to solve these problems on paper with a pen or a pencil. Okay, let's move on to another problem. Same goal. Can we find the solution to this system now, or demonstrate that there is no solution? Again, I recommend you pause the video and go ahead and solve on your own before moving forward. Okay, we're going to take exactly the same approach using standard techniques of Gaussian elimination. We begin, as always, with the first row, focusing our attention on the leftmost column. We want to use this 3x as a pivot to eliminate below. Here, coefficient of a 3 in the first row, of a 1 on the second, and a 2 on the third, means we want to subtract 1/3 of the first equation to eliminate the position below. So subtract 1/3 of equation 1 from equation 2, and subtract 2/3 of equation 1 from equation 3 to eliminate the 2x. Working through that, for equation 2, we're subtracting 1/3 of equation 1. X minus x is 0. Y minus 2/3 y is 1/3 y. Negative z minus 2/3 z is negative 4/3. Sorry, negative 2z minus negative 2/3 z is negative 4/3 z. And for the right-hand side, 2 minus 1/3 is 5/3. For the third row, 2x minus 2x gives us 0. Y minus 4/3 y gives us negative 1/3 y. 0, remember the blank space here gets read as a 0. 0 minus negative 4/3 z is positive 4/3 z. And on the right-hand side, we have to have a 0 written here. 0 minus 2/3 is, of course, 2/3. Okay. You already might notice something here, looking at these two equations and recognizing a similarity between them. But let's recast this and move forward anyway. So what would we, taking a look at what our system looks like right now, we have used this first entry as a pivot to eliminate everything below, isolating x in a single equation. So we move over to the next variable, down. We want to use this value as a pivot to eliminate below. The third row, the coefficient of y is simply negative the coefficient of y for the second row. So adding the second row to the third will eliminate this position. Negative 1/3 y plus 1/3 y is 0. Plus 4/3 z minus 4/3 z is 0. Negative 2/3 plus 5/3 is 3/3, or 1. Right away, we should identify that this is a problem. We have an inconsistent solution. We have an answer. This last equation says 0 plus 0 is 1. This is obviously not possible, and this tells us that we have an inconsistent system. This system has no solution. Anytime we get a 0 equals 1 in Gaussian elimination, this indicates we have no solution to the system. We did not, in fact, have to take this last step of Gaussian elimination. We could have identified in this, in the previous step, we could have identified that this row and this row had left-hand sides that differ just by a negative sign. We have plus minus 1/3, minus plus 4/3. They differ only by a negative sign. But these differ by more than just a negative sign. The left-hand sides are are scalar multiples. The right-hand sides are not the same scalar multiple. Cannot be a solution, as we identified it. Okay. Let's move on to one more example. Again, we want to find the solution to this system or demonstrate that a solution isn't possible. Once again, I recommend that you pause your video, work through the problem on your own, and then resume to compare to the solved solutions. We're going to take the same approach, working through standard Gaussian elimination. But one thing that we will note here, that as soon as we try to do that, we hit a hiccup. We look at the first equation, the first column, the top leftmost entry, but we don't have anything there. We're missing this entry. We can't use that as a pivot. What do? We swap rows. There is a pivot variable immediately below, so we simply exchange the position of these two, and we should do this. It's for working formally through the process of Gaussian elimination. We should rewrite this system in this new order. Right? After we've rewritten in this new order, then we carry on. We have a pivot variable. We wish to use this to eliminate below. Anytime we do a swap, at least one row will already have been eliminated. That's the whole reason we had to do a swap. So in this case, the only thing we need to do is to subtract the first equation from the third to get rid of this entry. X minus x gives us 0. 3y minus y gives us 2y. Remember, there's an implicit 0 here. 0 minus 2z is negative 2z. 1 minus 2 is negative 1. You also might see something already here. These two equations are identical. If you notice this, you can immediately say identical equations. I can remove one of them. If you do not notice that, we can move forward using the standard approach of Gaussian elimination. We've already eliminated downward in this position, so we move down a row over to the right and focus our attention now on this pivot. We want to eliminate below. These have the same coefficients, so we simply subtract the second equation from the third. 2y minus 2 is 0. Negative 2z minus negative 2z is 0. Negative 1 is 0. We get a row of all zeros because, as we already noted, these two equations are exactly the same. And if you subtract identical equations, you get 0 equals 0. When we have a row of 0, 0 equals 0, we don't stop. We can ignore this row and eliminate it from our consideration, but we don't need to stop. It's not the same problem that we had in the previous case with a 0 equals something non-zero. This is not an inconsistent equation. It's just not a very informative equation. At this point, we now can recognize that we have our upper triangular form. We have a pivot in the x position of the first equation, a pivot in the y position of the second equation, and we don't have any other meaningful equations. This tells us then there's still a z. Z is not a pivot in any equation. Z is a free variable. Anytime we have a free variable, this means we will have multiple solutions. We aim to solve for the pivots, x and y, in terms of the free variable z. Back substitution gives us that solution. So, back substitution starts with the bottommost equation. Identify the pivot of that equation and try to solve for it in terms of the free variables in this case. Move the negative 2z over to the right, gives us 2z minus 1, then divide through by 2 gives us z minus a half. Once we have a value for y, we can substitute it into the previous equation. And here I've just, for clarity, separated out the solve step and the substitution step. It's fine to put them in one step. And so y becomes z minus a half. We have our solution for y in terms of z. We now move up an equation, over to the left, focus on the next pivot of x, and try to solve for that. We have z minus half plus 2z is 3z minus a half. Moving all of that over should actually give us, negative 3z plus 5 halves. And for x and our previous value for y. We have x and y in terms of our free variable. We can leave it in this form. It's sort of often cleaner to write this in a parametric sort of form for our vector. Our solution is x, y, z equals, again, this same error here, negative 3t plus 5 halves, t minus a half, and t, where t can be any possible real value. The free variable, z, which we've substituted with the symbol t, can take on any possible number. We looked here at 3 different examples, 3 variable systems of 3 equations, one where we had a unique solution, one where we had no solution, one where we have multiple solutions that we represent with a parametric solution. In the next worked equation video, we'll go through a few more examples, larger systems, more complicated systems, but where we use the augmented matrix form to simplify and reduce the complexity of working through such problems by hand. Thank you, and goodbye.